Unit 3 Chemistry, Chapter 8, Part 2, looking at K values. So if we remember, K tells us the extent of the reaction. So it's essentially simplified concentration of the products over the concentration of the reactants. Remember, when we're actually working out, it's products to the power of their coefficient over reactants to the power of their coefficients. If we have a K value which is bigger than 10 to the power of 4, so bigger than 1,000, then we would say that at equilibrium the mixture is mostly products. Yeah, so it's basically almost to completion. If it is less than 10 to the negative 4, yeah, so less than 0.0001, then it's basically all reactants. Basically that reaction didn't hardly happen at all. Somewhere in the middle, we'd say there's a significant amount of both reactants and products at equilibrium. So, if we're calculating it, normally an equilibrium calculation would give you the initial concentration of everything. Now when I say it'll give you the initial concentration of everything, that might mean that it says into a vessel we put some potassium nitrate, add water. Okay? If it doesn't mention the products, then you assume their concentration is 0. Okay? The other thing it'll normally tell you is the equilibrium concentration of just one thing. Okay? You will then need to calculate the rest of what we need to do our K calculation. Basically, we need to know the equilibrium concentration of everything. So we use normally something called an icebox, where I stands for your initial amount, which is given to you in the question. C is the change amount, which we're going to find out using some stoichiometry. E is your equilibrium amount and the change. And then you can use the volume to calculate the concentration and therefore calculate K. So, if we think about this same equation as we were looking at before on the graph, it's written the other way around, but that doesn't matter, because remember this is equilibrium, so it can go either way. Okay, and that's the way around it happens to be written in this equation. So this at equilibrium is established at 440 degrees C. Why is it telling you the temperature? Well, because K is specific for a given temperature. Okay, you're not going to use that temperature in your calculation, it's just setting the context. It tells us we've got 1 mole of HI, so I'm going to put that in as my initial concentration of HI. It doesn't mention hydrogen gas or iodine at all, so I'm going to say their initial concentrations are 0. So all this black stuff is what it gives me in the question. And then it says it's found that HI has undergone 22% dissociation, so I'm going to put that in as well. Okay. 22% dissociation means 22% of what we started with here has broken up to make these. So it's gone down. It's a decrease in concentration. Can't go up because we don't have any of these to make it. And it's gone down by 22%. 22% of 1 is 0.22. So it's gone down by 0.22 mole. Okay? So using that, I can then find the equilibrium amount, okay, which is 1 minus 0.22, which is 0.78, and it's a 1 litre vessel, so my concentration is the same as my amount here. Okay? Then I think about my H2 and my I2. Now here I've got a 2 to 1 ratio. So each time I've got 2 moles of hydrogen iodide breaking up, I'm going to make 1 mole of hydrogen and 1 mole of iodine. So just as with any other stoichiometry, I'm going to use my ratios. But I'm going to use my ratios and I'm going to use this number as how much is actually reacting. Not this, because I know that not all of that reacted. That's the whole point of equilibrium. So this is how much actually reacted. So as always, we do how much we want over how much we've got. So want over got is 1 over 2, so we're halving it. So these ones go up by 0.11 mole, up by 0.11 mole, to find my equilibrium amounts and then my equilibrium concentrations. Now look here, I'm putting in the same number over and over again. Yeah, you're best to set it up this way. Sometimes you'll find that your volume is not 1 litre, so your equilibrium amounts and your concentrations are going to be different. Also, sometimes you'll find that you do have an initial amount of one of these. So you would need to add it, so your change and your equilibrium amount can often be different. So that's why we always set it up with the full boxes, even though sometimes we end up writing the same number again. Now I've got these equilibrium concentrations, now I can put it into my K expression. So K is equal to the concentration of each of the products, square brackets, remember, means concentration, over the concentration of my reactant. Now that's got a coefficient, that's got a 2, so that means I'm squaring it. Okay, plug in the numbers from my icebox. So I've got 0.11 squared, basically, over 0.78 squared, which gives me 0.0199 mole to the minus 1 I've written. I've hesitated there because actually that should have no units, because the concentration of each of these is in mole per litre, and you got mole per litre squared over mole per litre squared, so it will cancel out. And if that sounded horribly complicated, don't worry, because you're not assessed on K units. Okay. Now, in the next video, we'll look at how we can change K values.